Hello everybody, let's look at some examples from the 1.7 homework. The first one I want to look at, this is number 4. And the reason why I picked this one is because there's more to it than just using the chain rule, right? I have two different functions that are being multiplied together, so I'm going to end up needing the product rule as well. So why is this in my chapter that's dealing with the chain rule? Well, if I look at this function specifically, that one requires chain rule because you have a function inside of a function. So this problem gives me a chance to do both of those at the same time. So let's try it out. Well, if I look at finding my derivative, the first thing I kind of run into is the fact that I've got these two functions that are being multiplied together. So what I can do first is I can recognize those as my two different functions for using the product rule. So x squared is going to be my first function, g of x, and the square root of 2x minus 3 is going to be my second function, h of x. In order to use the product rule, I need the derivative of both of these. So the derivative of g of x just gives me 2x. And the derivative of h of x, well, this is where I need the chain rule, because now I have a function inside of another function. So to help me out, I can rewrite this as 2x minus 3 all raised to the 1/2 power, right? Whenever you have a root function, you can rewrite that as an exponent of just a fraction exponent, because that helps me actually use the chain rule. So now when I want to find the derivative, I'll take the derivative of the outside function, which is this 1/2 exponent piece, and I get 1/2, keep the inside function the same, and then I subtract 1 from the exponent, which gives me negative 1/2. So that's the derivative of the outside function. I left the inside function the same, but now I can multiply that by the derivative of the inside function. Well, what's the derivative of that inside function? That's just linear, and so the derivative is just whatever the slope is. Perfect. That looks kind of ugly, but this actually simplifies, because what's 1/2 times 2? That just equals 1. And so this just simplifies to 2x minus 3 raised to the negative 1/2. And just to clarify, right, if you think about exponent properties, what a fraction exponent actually means, what a negative exponent actually means, I could even simplify this by further by writing it like this: 1 over the square root of 2x minus 3. The square root is because it's raised to the 1/2 power. The reason why it's in the denominator is because it's the negative 1/2 power. So to recap, what we've done so far is, because I had two functions being multiplied by each other, I defined what each of my functions were, g of x and h of x. I found the derivative of both of them. And now I'm ready to actually use the product rule to put this all together. I'm going to move this down a little farther so I have more room. Product rule tells me that I take the first function and multiply it by the derivative of the second function, and then I reverse it. I take the second function, square root of 2x minus 3, and multiply it by the derivative of the first function. And there's my answer. Now, there's maybe a little bit more simplifying that I could do, but when you're putting this in Pearson, you don't have to simplify it. And I would actually encourage you just to go ahead and put it in like this so that you don't end up getting the problem wrong because you simplified wrong. But that takes care of number 4. Okay, let's move on to the next one. Okay, the next one I want to look at, this is actually number 7 from your homework. And I wanted to look at this one just because this one might be a little confusing with the different notation and, of course, the fact that it's our applied problem here. But if we read through what this is actually asking, so first of all, it tells us, okay, if 1,200 is invested at interest rate I, compounded annually, in 3 years it will grow to an amount A given by this function. A is equal to 1,200, right? There's my initial value. Multiplied by 1 plus I, there's my variable, raised to the third power. Part A asks, hey, find the rate of change. And then it has this symbol. Well, hopefully this looks familiar. Remember, this is just Leibniz notation, and all it means is I want the derivative. Well, how does that connect to this? Remember, that's what a derivative is. A derivative is an instantaneous rate of change. So it makes sense that they'd have both of those. That's all a derivative is. So that's what it wants me to do. It wants me to find the derivative of this function in terms of that I variable. Well, why is this in 1.7? Because I have a function inside of this cubed function, inside of this, right? I'm raising that whole function to the third power. So this requires chain rule. So if I want to find dA over di, I'm going to take the derivative here. What do I do with this 1200? What do I do with this piece right here? Well, this counts as a constant multiple, and according to my constant multiple property of derivatives, I can just keep that 1200 there and focus on the derivative of this second part. So now that I'm at the second part, here, let me rewrite it over here. I can recognize that this is a function inside of a function, so I need to use the chain rule. So I'll take the derivative of this by just moving the 3 down, keeping the inside the same, and subtracting 1 from that derivative. Subtracting 1 from the derivative, and I get to the power of 2. And then I need to multiply by the derivative of the inside function. What's the derivative of that inside function? 1 plus I. Well, it may not look like it, but that's really just a linear function. What's the slope? What number can I put in front of I if I don't see one there? I can always just put a 1 there. And so the derivative of that inside function is just 1. Makes for a fairly simple derivative, even though I technically use the chain rule. So now that I have that derivative of just that 1 plus I raised to the third power part, I can go ahead and multiply that on to what I already had, to that constant multiple. So I get 3 times 1 plus I raised to the second power. I'm not going to worry about putting that times 1 there because anything times 1 just stays the same. Perfect. Now, you can simplify if you want. This simplifying is really not too bad. It's just 1200 times 3, so that gives me 3600 times 1 plus I squared. And there's my derivative of my function. So this one definitely looks complicated, but it's really not too bad, mostly because the derivative of that inside function is just 1. So that takes care of part A. What about part B? Interpret the meaning of this. Well, remember, what is this? It's a rate of change. It's how something is changing. Well, what's actually changing? What's actually changing? What variable are we paying attention to? We're paying attention to this variable A. What does A represent? It's the amount of my investment. So this is how the investment amount is changing as something else changes. What's the independent variable here? In this case, that independent variable is I. It's the interest rate. So this is how the investment amount is changing as the interest rate changes. Now, if I wanted to be a little bit more specific here, notice that 3-year time is fixed. And so I could add in how the 3-year investment amount is changing as the interest rate changes. But the important thing here is the derivative measures this rate of change, how the dependent variable, in our case the investment amount, how that investment amount changes as the independent variable or the interest rate changes. How does changing the interest rate change the investment amount? Well, perfect. So those are 2 examples from the 1.7 homework. If you still have other questions on the other problems, please just reach out, send me an email, let me know, and I'll get back to you. But good luck, and I'll see you in the next video.